We're in the demo lab with Lonnie, where he set up a photoelectric effect experiment. He has white light impingent on a metal, and the energy of the photoelectrons emitted are shown on the meter at right. If he puts a red filter in the path, now only red photons can strike the metal, and you can see they do not have sufficient energy to eject photoelectrons. If we go to higher energy photons, say go to yellow light, that's shorter wavelength and higher energy photons, they may be able to eject photoelectrons. And indeed, photoelectrons are emitted, but with a relatively small energy. If we go to higher still photon energy, green wavelengths, that's shorter wavelength still, higher photon energies, we can see photoelectrons emitted at a higher energy. Now we can still go to higher energy photons. Blue photons, photons in the blue region, are the highest energy visible photons, and Lonnie has a blue filter that will pass only blue photons. Putting the blue filter in the path shows photoelectrons emitted at the highest energy. So here's an example of the photoelectric effect.
The quantum theory was proposed by Max Planck. According to this theory, radiation from a source is not emitted continuously, but it is emitted in packets or bundles of energy. These packets are called quanta or photons. If the radiation is of frequency f, each quantum has energy, where h is Planck's constant. Thus, energy of photon equals to E equals to hf. The energy is emitted in a discontinuous manner. This is contrary to the classical theory, which assumes that emission of energy is a continuous process. In the interaction of radiation with matter, the radiation behaves as if it is made up of particles. These particles are called photons. Each photon has energy which is given by E equals to hf equals to hc over lambda. All photons of light of particular frequency has the same amount of energy associated with them. The increase in the intensity of light increases the number of photons per second through a given area, but the energy of each photon will be the same. Photons are electrically neutral and are unaffected by electric or magnetic fields. Photons travel in a straight line with the speed of light, but show diffraction in certain conditions. The momentum of each photon is given by P equals to E over C equals to hf over C equals to hf over V lambda. The wavelength of photon changes with the media, hence they have different velocity in different media. The rest mass of a photon is zero. Its kinetic mass is given by m equals to E over C squared equals to hf over C squared equals to h over C lambda. In photon-particle collision, such as photoelectron collision, the total energy and momentum are conserved. However, the number of photons may not be conserved in a collision. The photon may be absorbed, or a new photon may be created. On the basis of Planck's quantum theory, Einstein derived an equation of the photoelectric effect, known as Einstein photoelectric equation. Einstein assumed that light consists of photons or quanta of energy. Energy in each photon is hf, where h is the Planck's constant, and f is the frequency of light. Each incident photon collides with an electron inside an atom and gives all its energy to the electron. Part of this energy is used by the electron to come out of the surface of the metal, and the remaining part is the kinetic energy, with which the electron is emitted. The minimum energy required by an electron to come out of the surface of the metal is called the photoelectric work function of the metal. The remaining energy is the maximum kinetic energy of the electron, with which a photoelectron will be ejected. Thus, maximum kinetic energy of electron equals to energy of photon minus work function. In the photoelectric effect, the most loosely attached electron of an atom of photosensitive material is removed. The minimum energy required to free an electron from the given surface is called the photoelectric work function of the material of the surface. The work function is the characteristic property of the metal surface. Mathematically, work function is given by work function equals to h times f to the sub-zero. Let m be the mass of electron and V max be the maximum velocity of photoelectron by which it will be ejected. Therefore, we have 1 over 2 mv squared equals to hf minus the work function. And we can now rearrange the function. And since hf to the sub-zero equals to the work function, therefore we can rewrite the function as hf equals to hf to the sub-zero plus 1 over 2 mv squared. Again, we can rearrange the function, and finally we get 1 over 2 mv squared max equals to h times f minus f to the sub-zero. This equation is known as Einstein's photoelectric equation. If the frequency of incident light is less than the threshold frequency, photoelectrons are not emitted. The number of photoelectrons emitted per second is directly proportional to the intensity of incident light. Thus, the photoelectric current is directly proportional to the intensity of incident light. If the intensity of light is more, the number of incident photons on the surface are more. Due to the increased number of photoelectrons, the rate of photoemission increases. Hence, the strength of photoelectric current increases. Thus, we can conclude that the photoelectric effect is directly proportional to the intensity of incident radiation. By Einstein's photoelectric equation, this equation does not contain the term of intensity. Thus, we can say that the maximum kinetic energy of photoelectron is independent of the intensity of incident radiation, but depends upon the frequency of incident radiation. And if the frequency of incident radiation is increased, the kinetic energy of photoelectron also gets increased. The photoelectric effect is an instantaneous process. There is no time lag between the incidence of light and the emission of the photoelectrons. In other words, the surface begins to emit photoelectrons as soon as light falls on it. Also, the emission of photoelectrons stops at the moment incident light is cut off. When radiation is incident on the photoemitting surface at that instant, the whole energy of the photon is transferred to a single electron in one go. Thus, the electron gets emitted without any time lag, and the photoelectric effect is the instantaneous process. Now, let's look at an example question. When radiation of certain wavelengths shines on the cathode of the photoelectric cell, the photocurrent produced can be reduced to zero by applying stopping potential of 2.63 volt. If the work function of the photoemitter is 4 eV, find the wavelength of radiation. So what are being given in the question is the stopping potential, the work function is 4 eV and can be converted into 6.4 times 10 to the negative 19 joule. And the speed of light in vacuum is 3 times 10 to the 8 meters per second. And the Planck's constant and the charge of electron, these two are constants. Let's now look at the solution. The maximum kinetic energy is equals to HF minus the work function, and is equal to hc over lambda minus the work function. Also, the maximum kinetic energy is equals to E times the stop potential. So therefore, we have the equation E times the stop potential equals to hc over lambda minus the work function. Now we can put all the values inside. And finally, we can calculate the lambda equals to 1.871 times 10 to the negative 7 meters.